Okay, so now we're going to see a different kind of network, which is these convolutional networks. I'm going to talk a bit what a convolution is, and I'm going to talk about what a convolution is, how we can create these convolution layers and stack them in networks, and then talk a bit about an important part in convolutional networks, which is pooling, and we're going to see how to do classification with convolution networks, and I'm going to introduce the carriage interface, so that from now on we are not going to program things directly at the level of TensorFlow, but implement the networks at this higher level, because as we start getting these more complicated layers, we would have to spend a lot of time to code everything on the detail level, and this is much faster. And then I'm going to talk a bit about this week's exercise with the classification using convolutional neural networks. So a convolution mathematically is the integral of the product of two functions, one of which was shifted and inverted. So basically, the convolution of this function f with the function g at some particular time t is the integral from minus to plus infinity of f tau g t minus tau and with respect to tau. And this is commutative, so you can change which one gets inverted, so t minus tau and tau, and which one is first or second. This is very used in many applications, for example, in these linear time invariant systems, but from the definition itself, it seems something that is very strange and hard to understand, so it's better to look at an example. Suppose we have this linear time invariant system that is, for example, an iron bar, and we can hit it with a hammer and it will start vibrating. So linear because if we hit it twice as much, it will vibrate with twice the amplitude, and time invariant because it doesn't matter when we start counting the time, when is the reference. All that matters is when the hammer hits, then it starts vibrating. So the response is the same no matter where you start counting the time, the coordinates there for the time. Now imagine that we want to know how the bar will oscillate if we hit it twice with a hammer in a quick succession. So this is 0.2 seconds in difference, and we are giving two quick taps with a hammer. Now we know how it responds to one hammer tap, but this would be more complicated because the second tap will hit somewhere here, and so you will get a mixture of two. And this is where the convolution helps us solve this problem. So we can take the inverse of the symmetric of the response, and now we can use the convolution operator to compute this product of the integrals at different time points, at different coordinates in time. So when we are here, since this is 0, the product of the two will be 0 here, but then when we reach a time shift that corresponds to the first hammer strike, then the product of the two functions is no longer 0 here, and so the integral gives us a higher value. But then this matches also with the second hammer strike, and what we get here after the convolution is the shape of the oscillations of the bar when we hit it with the two hammer strikes. So this is one way of imagining what the convolution operation is good for. But for our purposes, we can turn this around and look at it in a different way. Suppose we have this signal here, and we have some strange pattern that can occur, and we want to detect when that pattern occurs. We can also use convolution for that. If we create a detector, which is, this would be the detector function with the right inversion and so on, but when we apply the convolution operator here, we have these products here that when the time shift has these values, the function the result of the convolution is low, but as we start overlapping the pattern with the detector, we start getting higher values here, and this peak indicates where the pattern really matches the detector in our signal. So one way we can imagine convolutions is a way of detecting patterns in data, and this is very useful for neural networks because that is often what we try to do. An important thing here is that we don't care when the pattern occurs, so in which position along this coordinate the pattern will occur. It will be detected whenever it occurs. So our pattern detector is going through the data and it's going to detect the pattern wherever it appears. This is very different than what you would have if you fed this vector here into a dense layer, because these peaks will now feed into specific weights of the neurons and not to other weights, and so it would not be independent of where the pattern appears. So basically, if you think about when to use convolution layers or not, we use convolution layers when we don't care where the pattern appears in our data, and we use dense layers when the position is important. So this is for the continuous version with the integrals. If you have a discrete set of values, for example, a vector, a matrix, something like that, you can do the equivalent with the discrete convolution. So basically, instead of an integral, you have a sum of these products. And we can use this kernel here, a set of weights that we can learn, that we can adjust to apply to the input. And we can imagine that we have a set of weights in a small window, and everywhere else it is 0. So it will be a function like this one that we have here, the detector, that has this set of weights, and everything everywhere else it is 0. So we only need to focus on this window, and we run through the input with that detector. So this, since this would be, for example, a matrix of weights, if we are in the discrete domain, that we are multiplying by the input, that is the notion of kernel, is a matrix that you are multiplying by the other matrix. So basically, to do this operation here. In practice, for a convolutional neural network, the input is finite, but usually it's much larger than the kernels that we are using. So we can imagine in theory that it will be an infinite input with non-zero values only on a small range, everywhere else it's 0. We can imagine the same thing for the kernel, but in practice it's like taking a large tensor and a small tensor and doing this multiplication by scanning the kernel over the whole input. And this is how we can imagine the convolutional layer to be. Now, one detail here is that we can represent this convolution between the input and the kernel as we having the coordinates on the input, and we shift the kernel relative to the input, or the input relative to the kernel. So basically, in convolution, when we are imagining what we're doing, we are only considering that we are shifting the kernel relative to the input, because the other way around it would be confusing. And basically, we often use this notation. We are starting the kernel at some position ij, and then we are doing the operations from then to the end of the kernel on each dimension, and then we move the kernel to another position ij and do that again. Another thing, also another detail, is that this inversion here, using the symmetrical one, that is important mathematically for convolution so that it's commutative. But for our particular case, we don't really care, because we are learning these parameters and it doesn't matter if they are in that position or mirrored. So the way we represent things, typically it's like this. We are starting on coordinate I and j. For example, for an image, which is a two-dimensional input, we start at some particular pixel of an image with this coordinate, and now we're going to compute the sum of the products of each value on the image and the corresponding position on the kernel, and we're going to do that for the whole size of the kernel. We are not inverting coordinates here, so strictly speaking, this is no longer a convolution, it's a cross correlation. But this is irrelevant because inverting the order would just mean changing the position of the values on the kernel matrix, and we don't really care about that. So, strictly speaking, in convolutional layers we are using cross correlations, but we call it convolution because it ends up being the same thing in practice. Okay, so this is the theory, but now let's look at why this is good for neural networks in this particular case. So there are three big advantages of convolutional layers with respect to dense layers. One is that we have a greater sparsity, so we don't have those dense connections, we have much fewer connections between the layers. The other is that parameters are shared along the whole layer, so we have, with the combination of these two, far fewer parameters on convolutional layers than we would have on dense layers. In addition to that, we have this equivariance, which is what we saw previously. If you have that detector, it will give you a peak in the position the pattern appears. If the pattern shifts, you have exactly the same peak, but now in a new position. So basically, the output of the convolutional layer will change correspondingly to how the input is in translation. If we shift the input to the side, the output is equivalently shifted to the side. So let's see this in a bit more detail. Imagine that we have a dense layer here connected to the input, and for each neuron on the dense layer, we have weights connecting to all the values in the input. With convolutional networks, we generally have one receptive field that corresponds to that size of the kernel that is much smaller than the size of the input. So this particular neuron will only have weights for these values on the input and not to the whole size of the input. And this would be the kernel that we are using. So one advantage is fewer connections between input and the convolutional layer when compared to the dense layer. Note, however, that even though this neuron here has a small receptive field, if we stack convolution layers, so if this one is this convolution layer is receiving the output of this layer here, even though each neuron here only has a receptive field of 3 values here on the input, this one has these 5 values here because it's looking at the outputs of these neurons in the hidden layer here. And we can keep stacking, and so as we keep stacking convolution layers, the neurons in deeper convolution, in deeper layers, will receive information from a broader part of the input that we are feeding into the network. Another advantage is this parameter sharing, or if you want to imagine, we can imagine that this is only one neuron that is scanning through the input in the convolutional network, or we can imagine that we have all these neurons in the layer, but they are using the same parameters. So this connection between x1 and neuron s1 will have the same weight as the connection between x2 and s2, and so on, because this is that detector kernel that we can imagine is sliding here always with the same weight. So not only compared to a dense network do we have fewer connections, but also they are sharing the parameters, so the parameter is the same. Or if you want, you can imagine that it's only one neuron that is sliding through the input, always using the same parameters. So as you can see, you cut down drastically on the number of parameters if you go from one dense layer to a convolutional layer. The equivariance property, we can imagine it easily here. So suppose we have a very simple kernel that just subtracts from one pixel the value of the pixel on the left. So basically this gives us an edge detection that is very negative when the pixel on the left is a higher value than the pixel on the right, but when it shifts to the other kind of edge, it becomes positive. So you can have something like this. This detects passages from white to black, and then a key from black to white to black to white, and so on. The equivariance property is this property that if we shift the image up, down, left, or right, this feature map will have the same overall pattern, but it's just shifted in the same way that the image is shifted. This is something that does not happen necessarily with a dense network, because if you shift the input, now you're catching very different weights for the same parameters, and the output can be completely different. It does not change in the same way as the input was changed. But with convolutional layers, the feature map, which is the output of this neuron that we are scanning through the whole input, will be equivariant with the input, meaning that if the input changes in translation, in these dimensions where we are sliding the kernel, then the output will simply shift in the same way, but it still retains the rest of its properties. Okay, so let's see how this works in practice when we are implementing a convolutional layer. The receptive field is the region of the input where the neuron is getting the values. So it will be the size, correspond to the size of the kernel, and we'll have the values that are multiplied by the kernel of this neuron. The name receptive field comes from the visual cortex, because there are neurons in the visual cortex that correspond to specific parts of the retina, and different neurons correspond to different parts, so that is the receptive field of the neuron. And now let's imagine that this neuron here has a set of weights. They are the red values here. You don't need to be able to see them from there, but they are zeros and ones here. And when we place the receptive field of this neuron in the corner, for example, we do the operation with these 9 values, and we get a 4 there. So the sum of all the products here. The same thing for these 3, these 4, these 2. We are sliding over the input with this neuron, and we are getting the different values. So these values here, the ones in red that are the weights of the neuron, are the kernel. This output here is the feature map, which is the map we obtain when we apply the kernel to the whole input. But we can have more than one of these neurons in our convolutional layer. So each of these neurons will produce its own feature map. It will have a depth here. And we can represent this like this. This can be something like a color image, for example. If it's a color image, it will have 3 channels, red, green, and blue. Each of the neurons here will receive inputs from the whole 3 channels for a specific receptive field, and it will scan that receptive field, and it will generate one feature map with a width and a height that depends on the size of the kernel and the size of the image in the input. But then we have several neurons here, and each one will produce one feature map. So we have a stack of feature maps here, and this will give us the depth of the tensor that is coming out of the convolution layer. So basically we have these parameters here. We have these number of filters, because after we apply the convolution operation, this is a linear transformation. We are just multiplying by values and summing everything up. We now need to do something non-linear to that, otherwise stacking convolutional layers would not help us. So after we do this, we have an activation function, and that way we produce the feature map. So the feature map comes out of passing the neuron over the input, doing the convolution in that way, and then applying the activation function to what comes out of the convolution, and we have a feature map there. Usually, if you are using hidden layers here, you use rectified linear units. This is what works best. Now, there are several parameters to a convolutional layer that you need to specify. One is the depth here, or the number of filters. We can say that one filter is this mechanism, so to speak, that passes the input through the convolution and then the activation function to give us the feature map. So the filter is this whole process of going all the way through the convolution to the activation function. And we can have several filters in the convolutional layer, and this will give us the corresponding depth to the tensor that is being output from the convolutional layer. Another thing that we need to specify is the stride, which is how the receptive field jumps. Here you have an example of stride 1, meaning that the receptive field of the neuron is stepping one position at a time. Here you have an example of stride 2. It's stepping 2 positions at a time, so the output feature map will be smaller and it's skipping some of the locations there. So by adjusting the stride, you can adjust a decrease in the size of the feature map because you are skipping positions in the input. Another important parameter is padding. If you see in this example, as we scan the input with our kernel, even though the input is 5 by 5, the result is 3 by 3, because we cannot step outside the input, and so the center of the kernel cannot reach all the positions in the input. This can be, this problem can be eliminated if we add padding, for example, adding zeros all the way around the input, so that now the kernel can reach all the positions of the input and the feature map has the same dimension as the input. So padding allows us to keep the same dimension of the feature map. If you don't use padding, then you're cutting the corners and the edges and you shrink a bit the feature map relative to the original size. Here is an example of a convolutional network used for classification. We have here convolution, rectified linear units, convolution, rectified linear unit, then pooling. I'm going to talk a bit about this. Then more stacks like this, more, and then everything is flattened and passed through fully connected layers, through dense layers, to get the classification at the end. So the idea is that these convolution layers are learning to find the correct detectors for the patterns that are important for the classification at the end. And they, even though these first ones have a small receptive field, so they can only look at small details on the image, as we keep stacking them, the effective receptive field is going to increase because one neuron here can see, for example, 3 by 3 on this feature map, but this is in turn 3 by 3 on this feature map for each pixel, and for each of the pixels on that feature map, it's a 3 by 3 region on the image. So these things are increasing in a pyramid from the deep layers all the way to the input, so that these deeper layers can identify larger patterns on the image. Things like the headlights, the windshield, things like that, that can help them classify the image as a car. So basically, this is how you build a convolution network, by stacking the convolution layers. But another important part here is pooling. So pooling consists in aggregating the outputs of different neurons, so basically each region on the feature map, into a single value. So we usually do these convolutions. We use several filters to learn different convolutions at that level to find different patterns. Then we apply nonlinear activations so that we can stack these and have useful transformations along the network. And pooling at given stages aggregates values from neighborhoods on the feature map into single values. For example, here, this is an example of max pooling. We are doing a 2 by 2 pooling with a stride of 2. This means that we are looking at this window, then we jump 2, look at that window, we jump 2, and so on. And on each operation here, we take the maximum value, so from these 4, we take the 6, from this we take the 8, and so on. So max pooling, the idea is that if the pattern was detected in this window, we keep that value here to indicate that we found the pattern there. If it was detected here, we indicate that here, and so on. So this gives us the best output of the detector for each particular region. and it reduces the resolution with which we are seeing. So two things that pooling does is, one, it reduces the size of the tensors. It makes the representation simpler as we go along the network. And the other is it abstracts from the actual position where the pattern was found. So suppose that this was a detector for a wheel. It detected the wheel in this position here, something a bit like the wheel in this position, but we don't really care where exactly the wheel was detected. So we abstract from that, and we only remember that the wheel was detected somewhere around here. And now if we keep doing this, eventually we can reach a stage of our network where we only have a one-by-one pixel feature map with lots of different features, and it only tells us which patterns were detected somewhere around the image, and it doesn't matter where. So this is important. Whether we're dealing with images, this is the easiest one to imagine, but you can do this with sound files, for example, with three-dimensional CAT scans. It doesn't matter if it's 2D, 3D, 4D, but the idea is that pooling is also helping to abstract from the exact location of the pattern to a representation that only tells you the pattern is there somewhere around the image. So there are typical pooling functions are max pooling, average pooling, L2 norm, which is root mean square of the values there. And the idea is that each time you do pooling, you make the model less sensitive to shifts in the input. The pooling stride typically is equal to the size of the region. This is often how pooling is done. So this is an example. We have a pooling of 2 by 2. We also have a stride of 2 by 2 because we are moving, we don't have overlaps between the pooling windows. But in theory, you can do this with whatever combination you want. But generally, we are using pooling not only for abstracting the exact location, but also for reducing dimension. So using the stride equally to the pooling window helps us do that. If you use pooling with a stride of 1 and padding, then you can preserve dimension. So you can abstract from the position of the patterns while still retaining the same dimension on your tensor. This is not generally used, but it's possible to do. So for classification, typically we have these blocks or these layers of convolution. So this is an example from AlexNet from 2012. We have 48 filters here, 128 here, 192, and so on. And as we keep doing pooling, the size of the feature maps shrinks, but we are increasing the number of filters there, so we are increasing the number of detectors for the different patterns, and then eventually we reach a stage here where we only have these 13 by 13 feature maps, 128 of them. We convert this, we flatten this tensor into a single vector, and then we enter the dense networks for classification. So this is the general approach: use convolution, then flatten everything and feed into the dense network if you want to do a classifier. We're going to see in the next few weeks other things that we can do with convolutional networks. Okay, so for this week, the tutorial will be to build an image classifier using convolutional layers, and we're going to use the Keras API for that. So you can import the optimizer you want. This is the stochastic gradient descent, the basic one, but if you want to try the other ones, AdaGrad, Adam, and so on, just look up the documentation and you can experiment with that. Sequential is the class that creates the model. The sequential model works a bit like lasagna. You stack all the layers. It doesn't allow you to do anything else, but it works perfectly for that. So if you're trying to create a network where you just need to stack layers, this is the easiest one to do. We need the layers we're going to stack, so this conv2D is the convolutional layer for 2 dimensions. Max pooling 2D is the one for doing max pooling. We also need the dense layer for the classification part. This is what we've been using so far. It's called dense. But then you also need the flatten to pass from the convolutional part to the dense part. So after you leave the convolutions and before you enter the dense layer, you need to flatten the tensor so that it has only one dimension for each example. The activation layer allows you to put in the activations that you want. So normally when you put one layer, you can specify the activation, for example, sigmoid, relu, and so on. But some activations like leaky relu and such, you need to actually specify some parameters, and it may be more practical to use a specific activation layer for that. But there are different ways. You can look at the documentation for doing this. Batch normalization is that part I talked previously, where we are standardizing the output of each layer before putting it into the next one, and dropout implements the dropout regularization we saw previously. So the way you do this, you create a sequential model, and then you add one layer where you specify the shape of the input. The first layer needs the shape of the input so that Keras knows what the architecture will be. In this case, the input will be this fashion list example that we have here. So each image is a 28 by 28 grayscale image, and there are 10 classes of clothing here that we need to classify. So we are going to say that the input is a tensor of 28 by 28 for each example, and with only one channel in depth. If you had a color image, then you would have 3 channels of depth for red, green, and blue. In the case of grayscale, you only have 1. And we can say that we want, for this convolution layer, 32 filters, each one with a kernel of 3 by 3. This is the size of the receptive field on the image. We can use padding same. This means that the carriage will pad the input with zeros in sufficient numbers so that the output of this convolution layer has the same size as the input into the layer. So padding same preserves the size. It means that the feature maps coming out here will be 28 by 28. And since we have 32 filters here, we'll have a tensor of 28 by 28 with 32 of depth. And then we can add an activation rectified linear union. Here you can import different activations and experiment with leaky, relu, and so on. You can also put the activation as an argument there if you want. I'll leave that up to you, trying out different ways of doing this. This is all on the online documentation, but the important part is to understand how we're building this model. So basically, the sequential model has this add method where you add the objects with the layers. The first one needs the input shape, but from then on, Keras ignores the input shape argument because the input into each layer depends on the previous layer. It's the output of the previous layer. So now we just put one layer on top of another. There are things missing here, but this is an example of pooling. You can have several convolution layers, then pooling. By default, the stride will be equal to the pool size, so you don't need to specify here. And then you need flatten before going into the dense layer. The reason for this is that the dense layer needs to have one vector of inputs for every example, but the tensors we are outputting here have 3 dimensions. They have width, height, and depth, and so that doesn't fit in the dense layer, but flatten converts everything into a single vector. And now you can use batch normalization, you can use dropout to regularize the network, and you can experiment with this. So some details here. The consensus is that batch normalization should be applied after the activation function. The reason for this is that we are standardizing the input into the next layer. So after we did everything with one layer, we standardize and we put it in the next layer. Dropout should be done after all batch normalizations, because this is a bit tricky. Dropout is turning on and off neurons, and batch normalization is keeping a running average and the standard deviation of the inputs. So if you put dropout before batch normalization, you are making things messy for the batch normalization, and it may not work very well. So the general consensus, the recommendation is to use dropout after batch normalizations. One reason for this is that dropout needs to rescale the weights after training, but batch normalization will keep the same parameters it learned during training, so things will generally not match very well. Dropout may have some benefits in convolutional layers, but it's strange there, because when you're doing dropout on the dense layer, you are turning on and off neurons on the dense layer. When you do that on the convolutional layer, either you're doing that at the level of the filters and turning on and off filters, which may be a bit too much, or you're doing that at the level of the feature map and you're turning on and off parts of the feature map, which is also a bit confusing. So dropout is meant conceptually for dense layers, not for convolutional layers. You can use it in convolution and maybe it works, but it's a bit more confusing then. Now, to compile the model, after you wrote the whole model, and I recommend that you create a function that creates the model and returns the model object. This because you can then easily import this in another module on your Python code if you want to reuse the same model. But you also need to have the optimizer. So, for example, we can create the stochastic gradient descent optimizer like we did before. And now we call the compile method on the model, where we specify what optimizer to use, what metric we're going to use, and what loss function we're going to use for training. So remember, in this case, we have a multi-class classification problem. It's 10 classes, yes?
In the previous slide, what is the decay in the...
Okay. So this is another option that you can, thanks for asking, I forgot to mention that. You can check the documentation, but basically this is a way of reducing the learning rate during training. So we have a decay factor here, and basically you are multiplying the learning rate by that factor, or 1 minus a factor, I don't remember exactly, I have to look at the documentation, but it means that you use the full learning rate first, then after 1 epoch you use, say, 99% of the learning rate, then 99% of the previous one, and so on, and so the learning rate will decrease slowly, and this improves convergence because the same quick steps and large steps at the beginning may not be as appropriate at the end of training. So this is another thing that you can use in stochastic in these optimizers, which is to reduce the learning rate during training. And now here, this is the activation at the end. We have 10 neurons, and we use softmax because we have 10 classes. This will be the example. And we need to use categorical cross entropy because that's the loss function adequate for this type of activation. You can also include additional metrics. For example, in this case, classification, you can include accuracy so that you see what is the fraction of correctly classified examples in your classifier. And now, to train the model, you just call fit. You give the input to the model. This will be the training set, the X values, the labels that you want to predict, and then you can also give validation data. This allows the fit method not only to train your model, but then report to you the metrics on the validation data so that you can track training and validation error. And at the end, you can save the weights to a file. So this allows you to compile the model again and then load the weights, and you don't have to repeat training. You already have the parameters there, and you can reuse your model later. So I advise you to do this because next week we're going to use this model to do transfer learning for the NIST problem. After you compile the model, you can call summary, and this will give you a summary of the model, the different layers, the number of parameters, and so on. You can also include callbacks for TensorFlow, so you can for Tensorboard. Sorry, you can create these Tensorboard callbacks, and then, for example, use this to write the graph to the file and to write the different metrics to the Tensorboard logs, so that you can track while training how the training is going. So if you want, take a look at the callbacks that you have, but these are easy to use. You just add there when you're fitting the model, and then you can track everything in the Tensorboard as you did in the previous exercise. The fit method returns a history object that has this different, it works like, it has different attributes, but one of them, also called history, is a dictionary with the values over all the epochs of the metrics we asked. So if we have training and validation, it will give you the training and validation values. If you don't add anything else, it will only give you the loss function. If you have additional metrics, it will also give you the values of those metrics. Okay, so this you're going to apply to the fashionist. You have these grayscale images of 10 different classes of clothing. What you need to do is to load the data. This is in the data sets in Cache. So when you run this method here, load data, it will either load it from cache if you already have the data in your computer, or it will download it first. It's about 30 megabytes, so maybe you want to try this at home before coming here. But once you have the data in cache, it loads quickly. Now we're going to reshape this into the appropriate shape of the images and normalize so that we have values between 0 and 1. These are byte values, so they are between 0 and 255. We convert everything into float 32 between 0 and 1. And one additional thing that we need to do is to create the one hot encoding for the labels. So this, you can use the two categorical like we saw previously. So basically we are converting those integer labels here into those vectors with 0, 1, like we saw before with NIST. So this is what you need to do. It's similar to what we did in NIST, so only in NIST we wanted each image to be a vector of 768 because we were feeding into a dense network. Now we want it to be 28 by 28 with 1 of depth because we are feeding into two-dimensional convolutional layers. And now this is one proposal for the model. So you start with two convolutional layers with 32 filters, rectified linear units and batch normalization. Then you do max pooling, and then optionally you can try dropout, but dropout at this level is a bit confusing. So it actually seems to make the results worse. And then you do a second stack that is identical to the first, only it has 64 filters in each convolution layer. Then you can add a dense layer of 512 and then a softmax layer, and here you can use dropout of 50%. So we have a very large layer, but we are dropping half of the neurons at each batch so that we are averaging many different combinations. You can use the SGD optimizer or other, but this takes about 25 epochs. But after around 4 or 5, you already have some good results, but you may train it for a bit longer. And then save the weights after fitting, because we're going to reuse them next week. If you want, you can change these architectures, experiment with it, use different optimizers and so on. This is just a suggestion, but the idea is to play a bit with this to see the results that you get. So to sum up, we saw what convolutions are and how to use them in deep neural networks, and this example of classification with convolutional networks. You're going to do this week, and from now on we're going to use the Cache API. First the sequential and then the functional one, which is a bit more powerful.